Welcome to Oscillations. Today we are going to talk about forced vibrations and dissipative forces. And really it's just a formal discussion which generalizes the aspects that we've treated in the introduction in the introduction regarding the one-dimensional motion for a simple harmonic oscillator that may be damped or driven by an external force. Up to now, we have looked mainly at free oscillations, which imply an initial displacement of the system, which is then allowed to move by itself. However, external forces can continue to act even after the initial moment, leading to the so-called forced oscillations. And the frequency in that case is given by the driving force and not the resonant frequency of the system. Normal modes remain important for obtaining the amplitudes of the forced motion, and the normal coordinates obtained from free vibrations still simplify the treatment. So if we have the components of the force Fj corresponding to a coordinate eta j, then from equations 149 we can write the generalized force corresponding to a normal coordinate zeta I according to the transformation here, and the corresponding equation of motion is immediately the one given below. So what we have obtained is an inhomogeneous system of n differential equations that can be solved only if we know the dependence on time of these generalized forces corresponding to each of the normal coordinates. However, the variables are still separated, and quite frequently the driving force is sinusoidal, as is the case, for example, of the pressure generated by a sound wave impinging on a system in acoustics, and then the generalized force has the frequency of the sound wave. Another example is in electrodynamics, where a monochromatic light beam can impinge on a polyatomic molecule, and then each atom is subjected to an electromagnetic force having the frequency of the incident light. More generally, any periodic driving force can be represented as a Fourier series or a Fourier integral, and particular solutions of the system of equations can always be superposed to obtain the complete solution for a given generalized force. So we can write it as a periodic function having an amplitude of index 0 and a phase delta I, and then the equations of motion have these expressions where we just replace the generalized force with its periodic nature given in terms of a cosine function, and the period of the driving force here being omega, as opposed to the omega index I being the natural frequency for that specific normal coordinate of the system. Now, a complete solution will involve free modes plus a particular solution of the inhomogeneous equation. The former, so namely the free modes, can be made to vanish by a proper choice of initial conditions. This is due to them essentially being transients of the driving force, which can be removed either by turning the driving force on very slowly, so adiabatically, or by damping them out through dissipation. So then we can look for normal modes of the form here, where their amplitudes follow as these ratios, and then generally the eta j's will be linear combinations of these normal modes, and they will be presented as this kind of expansion. So each vibration is a linear combination of normal modes, and each of them occurring at the frequency of the driving force. Right, so this is the omega here. Now, the extent to which a normal mode is excited depends on the amplitudes of the generalized forces. So an external force can excite a normal mode only if it tends to move particles in the same direction as the given mode, and it also depends on the closeness of the natural frequency of that particular normal mode and the frequency of the driving force. when these two frequencies cross, the system exhibits a resonance, namely a large amplitude motion where the result 666, the one given here, breaks down. Furthermore, and this is a comment we've made previously as well, but given the structure of the denominator here, if the driving force is smaller than the resonant frequency, the oscillations are in phase, otherwise they are out of phase by pi. Now, for a periodic force, the Fourier integral is given here in terms of its Fourier transform g of argument omega. And then you can see straight away that the general solution of 661 follows immediately as this expression. So if you replace this in 661 and carry out the derivatives with this expansion of the force as a Fourier integral, you will see that the equation is automatically satisfied. When it comes to the presence of dissipative forces, the situation, the treatment is a bit different. Such dissipation forces tend to be proportional to particle velocities, and they follow from a dissipation function, where these coefficients Fij are symmetrical and they usually depend on coordinates. If the oscillations are small, it is enough to perform a Taylor expansion about the equilibrium position and retain the first constant term, exactly as in the case of the kinetic energy. Recall from equation 260 that 2 times F is the rate at which energy is dissipated. Hence, the Rayleigh dissipation function is always positive. And then the full equations of motion have the form here. So solving them would require a principal axis transformation that simultaneously diagonalizes the matrix corresponding to the potential energy, to the potential energy, to the kinetic energy, and to the dissipation function. Generally, this is not possible. However, if the matrix of the dissipation function is proportional to the particle velocities and mass, then this matrix will be diagonal whenever the kinetic energy matrix is, and then the equations reduce to those of the normal modes, which are written here. So if we look for normal modes of this general form for some unknown frequency, primed frequency different from the resonant frequency of the system, we find such characteristic equations which have the following solutions. So the primed frequencies are given in terms of a real part involving the resonant frequencies of the system and the effect of dissipation on that particular degree of freedom, and an imaginary part involving only the dissipation function. So these are complex frequencies where the imaginary parts imply exponentially damped motion, while the real part is just represents the frequency of the real oscillation. And if the dissipation term is small, then the oscillation takes place practically at the resonant frequency. So we speak of solutions of this form, which are just damped harmonic oscillations and a generalization to an arbitrary number of degrees of freedom from the problem of the damped harmonic oscillator that we studied in the introduction. So the general nature of this solution is always one involving oscillatory and damped motion, but it is much more difficult to obtain it if the matrix of the dissipation function cannot be diagonalized simultaneously with the matrix of the kinetic and potential energies respectively. So we can try a solution of 668 of the form here. So these the eta j, so for, let's see, for 668, yeah, we can write eta j as an oscillation of some unknown frequency omega, which we decompose into a real part, nu, and an imaginary part, kappa. And introducing this into those equations and solving, we get to the following characteristic equations. And furthermore, we can introduce this notation. So we can introduce gamma as minus the imaginary unit times omega, which expands into the formula here. And then if we put these two results together, we can find the matrix equation, or the whole set of homogeneous equations of the form here. And this will be solved non-trivially usually only for very specific values of either of omega or gamma. In any case, if we multiply it from the left by the adjoint of the eigenvector A, we can obtain this form of the equations. And we see that these are in effect quadratic equations for gamma, having coefficients of a form very similar to what we have seen back in equation 619. And as all operators are symmetrical, the matrix products are all real. So if gamma is a solution, so is its complex conjugate. And then their sum, based on the definition here, their sum is just minus 2 times kappa, which according to the equation here becomes this ratio. So then if we expand the eigenvector A in real and imaginary parts, we can solve for kappa to obtain the expressions here. Now, as the dissipation function is always positive, and since the kinetic energy is positive definite, kappa is always going to be greater or equal to 0. So the oscillations are always damped exponentially, but they can never increase. If the dissipation function happens to be positive definite, then kappa is always strictly greater than 0, and all modes are damped exponentially. The oscillation frequencies omega will be affected by dissipation, but the change will be small if the damping is not very large during a period of oscillation. The most complex situation arises when forced oscillations happen in the presence of dissipation. So then, assuming that the driving forces are oscillatory in nature, we get the inhomogeneous version of the equations that we have previously studied. So these are the equations of a motion for damping, but now also with free terms given by the driving forces. So we can try to look for general solutions of these equations of the form here for some amplitudes capital A of index j, and we will find this set of characteristic equations. And these are the inhomogeneous versions of the set labeled by 674, and their solutions follow from Cramer's rule. So the amplitude aj for A index j for each equation is given by this ratio, where the denominator is the determinant of the matrix having the coefficients of A index j in 681, and D having an index j is that same determinant, but having the jth column replaced by the column of the free vector. The denominator is of main interest here, as it may give rise to resonances. It is also the determinant involved in the secular equation of 674. Its roots are the complex frequencies of the free modes of vibration. And so if gamma and its complex conjugate are the roots of 677, then by the relation 675, if omega index I is a root of the omega, then so is minus its complex conjugate. if the system has n degrees of freedom, we can expand this determinant as the product shown here, where g is just some constant. And if the frequency omega can be represented in this form, then we can write this expansion as the kind of products shown here in terms of this expression for omega and the expansion of omega of the resonant frequencies in terms of their real and imaginary parts. And if we multiply this determinant with its complex conjugate, we should obtain something like the expression here. So the above is the denominator following from the rationalization of 683, leading to the separation of the coefficients A of index j in real and imaginary parts. The forced oscillations exhibit typical resonance behavior when close to the frequencies of free oscillations. So when these driving frequencies are close to the resonant ones, to the free oscillations. However, the amplitudes remain finite due to the presence of these damping constants, kappa. So as you see, again, it's a generalization of what we had seen when we looked at the damped driven harmonic oscillator. So the shift in resonant frequencies is small for small damping, as long as a resonance peak remains noticeable. Now, if the dissipation function can be diagonalized along with the kinetic and potential energies and the driving force is periodic in nature, then the forced vibrations for the normal coordinates are given by this kind of Fourier integral. And once again, you can check this straight away just by calculating the derivatives of these functions and plugging everything in the respective equations of motion. You will see that everything cancels out immediately. So we have made a summary of the basic problems that arise in the theory of small oscillations, but there are many aspects that we have yet to discuss, and some of them won't be a part of these discussions at all, as they are a bit too specialized for what I have in mind for this project. So for example, in the case of an arbitrary time dependence of the driving force, one can use the method of Laplace transforms to study the response of linearly oscillating systems. And the equations 680 are so the ones here. So the ones for small oscillations featuring both forced vibrations and dissipation. These are equivalent to the equations we found back in chapter 2, so equations 242. If we identify the matrix elements of the potential energy with capacitances, the matrix elements of the dissipation function with resistors, and the matrix elements of the kinetic energy with inductances, and the driving forces with generators of frequency omega. So they just become the equations from electrical circuit theory, where these kind of discussions find many applications. Some things that we will treat in more detail are aspects of nonlinear oscillations, but in the more advanced context of Hamiltonian mechanics, chaotic motion, and perturbation theory. And we will do this together with the theory of small oscillations about stable motion. We have treated these to some extent when we looked at the central force problem, but we did it in an intuitive way. So later on we will see the formal theory behind the treatment of such problems. And one very important aspect that we will discuss later is the problem of the oscillations of system having continuously infinite numbers of degrees of freedom. So continuous systems like non-rigid bodies. But we are going to do that in the context of Hamiltonian mechanics and also in the context of relativity theory. So those discussions will have to wait until we have developed these two formal aspects of classical mechanics. So in summary, we have studied the general problem of forced oscillations with and without damping. The problem of damping has been investigated in the case when the dissipation function can be diagonalized within the principal axis transformation, and we have also looked at a situation in which this is not possible. And lastly, in the final section of this chapter, we are going to discuss the damp-driven pendulum as an example of a problem going beyond small oscillations. But it's going to be a very short discussion. I just want to underline some of the main aspects of the problem, and it's not going to be a very detailed treatment at this point in time. In any case, with all that being said, I want to thank you very much for watching. I hope you found the discussion worth your time, and I will catch you later. Goodbye.